NEC Section 250.32b addresses grounding and bonding requirements for buildings or structures supplied by a feeder or branch circuit. This section is particularly relevant when dealing with multiple buildings or structures on the same property, especially when they have separate grounding electrodes. The answer is yes, the steel of the new building should be bonded to the existing building steel. NEC Section 250.32b requires that when multiple grounding electrodes are used, a bonding conductor must be installed to connect all grounding electrodes together. Even though the new building and existing building are structurally separated, they are still connected by piping and other conductive materials. This connection can create potential for ground loops and electrical hazards if the steel of the two buildings is not bonded together. Bonding the steel of the two buildings ensures that they are at the same electrical potential, reducing the risk of electrical shock and equipment damage. To bond the steel, a grounding conductor should be used to connect the steel of the new and existing buildings. The size of this conductor should be determined based on NEC Section 250.66, and the insulation should comply with NEC Section 250.134. When dealing with separate buildings or structures, understanding the specific requirements for grounding and bonding is essential to ensure electrical safety and compliance with the NEC. Now let's go into more detail about NEC Section 250.32, which covers grounding and bonding requirements for separate buildings or structures. This section applies when a building or structure is supplied by a feeder or branch circuit from another building or structure. It outlines the conditions under which a grounding electrode system must be installed at the separate building or structure and how the grounding and bonding connection should be made. NEC Section 250.32 addresses the grounding electrode system at a separate building or structure. It generally requires that if a building or structure is supplied by a feeder or branch circuit, a grounding electrode system must be installed at that building or structure. This grounding electrode system must be connected to a grounding electrode conductor that is run with the supply conductors to the separate building or structure. The grounding electrode system can consist of various electrodes, such as a metal underground water pipe, a metal frame of the building or structure, a concrete encased electrode, or ground rods or ground rings. NEC Section 250.32b provides an exception to the requirement for a grounding electrode system at a separate building or structure. This exception applies if certain conditions are met, including that the separate building or structure does not house livestock and that there is an equipment grounding conductor run with the supply conductors to the separate building or structure. If these conditions are met, the equipment grounding conductor can be used as the grounding electrode for the separate building or structure. However, there are specific requirements for the size and installation of the equipment grounding conductor in this case. NEC Section 250.32c covers the bonding requirements for separate buildings or structures. It requires that all grounding electrodes that are present at the separate building or structure must be bonded together to form a single grounding electrode system. This bonding is typically accomplished by connecting the grounding electrodes together with a bonding conductor. The size of the bonding conductor must meet the requirements of NEC Section 250.66. NEC Section 250.32d addresses the requirements for the grounded conductor at a separate building or structure. In general, the grounded conductor must be insulated and must be run with the supply conductors to the separate building or structure. The grounded conductor must be connected to the grounding electrode system at the separate building or structure. However, there are some exceptions to this requirement, such as when the separate building or structure is supplied by a feeder that originates from a separately derived system. The size of the grounded conductor must meet the requirements of NEC Section 250.24c. NEC Section 250.32e covers the requirements for the equipment grounding conductors at a separate building or structure. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. This helps to provide a low impedance path for fault current to flow back to the source, which can help to trip a circuit breaker or fuse and clear a fault. The equipment grounding conductors must be sized and installed in accordance with NEC sections 250.118 and 250.122. When dealing with separate buildings or structures, it is essential to carefully review and comply with all of the applicable requirements in NEC section 250.32 to ensure electrical safety and code compliance. Let's delve deeper into the specific aspects of bonding and grounding in separate structures as per the NEC, particularly focusing on the practical implications and methods for ensuring safety and compliance. When connecting separate buildings or structures electrically, the primary goal is to maintain a consistent ground potential between them. This minimizes the risk of voltage differences that could lead to electrical shock hazards or equipment damage. The NEC provides guidelines to achieve this, emphasizing the importance of bonding and grounding. The NEC defines bonding as the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Grounding, on the other hand, is the connection to earth or to some conducting body that serves in place of the earth. In separate structures, both are critical. Let's consider scenarios where separate buildings are supplied from the same service. If each building has its own grounding electrode system, NEC section 250.32c mandates that these grounding electrodes must be bonded together. This is typically achieved using a bonding conductor, often copper, sized according to NEC section 250.66. The bonding conductor ensures that all grounding electrodes are at the same electrical potential. For instance, if you have a main building with a service entrance and a detached garage or workshop, each with its own grounding electrodes such as ground rods or a U for ground, these electrodes must be connected with the bonding conductor. This prevents potential differences during fault conditions or lightning strikes. The size of the bonding conductor is determined by the size of the largest ungrounded conductor supplying the buildings. For example, if the largest ungrounded conductor is 200 amps, the bonding conductor would need to be a certain size based on NEC table 250.66, typically at least a number 6 AWG copper or a number 4 AWG aluminum. When running the bonding conductor, it should be installed in a manner that protects it from physical damage. This might involve running it in conduit or burying it at a sufficient depth. The path of the bonding conductor should be as direct as possible to minimize impedance. If the separate building or structure is supplied by a feeder or branch circuit and meets specific conditions outlined in NEC section 250.32b, an exception is allowed. Under this exception, a grounding electrode system at the separate building is not required if an equipment grounding conductor is run with the supply conductors and certain other conditions are met. These conditions typically include that there are no livestock in the building and that there is a means to disconnect all ungrounded conductors. In this case, the equipment grounding conductor serves as the grounding electrode. However, it's crucial to ensure that the equipment grounding conductor is adequately sized according to NEC section 250.122. For example, if the overcurrent protection device for the feeder is rated at 60 amps, the equipment grounding conductor must be at least a number 12 AWG copper conductor. The installation must also comply with NEC section 250.130, which covers the methods for connecting the equipment grounding conductor to the grounding electrode at the source. In some cases, separate buildings might be connected by metallic piping systems such as water or gas lines. These metallic paths can create a potential for ground loops if not properly addressed. A ground loop occurs when there are multiple paths for current to flow to ground, creating circulating currents that can cause interference or even pose a safety hazard. To mitigate ground loops, it is essential to ensure that all metallic piping systems are bonded to the grounding electrode system at each building. This is typically achieved by bonding the piping to the building's grounding electrode conductor or to a nearby grounding electrode. The bonding jumpers used for this purpose should be sized appropriately based on NEC section 250.102. For example, a common practice is to use a bonding jumper that is at least as large as the equipment grounding conductor serving the circuit that is likely to energize the piping. It's also crucial to ensure that any insulating fittings or couplings in the piping systems are properly bypassed with bonding jumpers to maintain electrical continuity. This prevents the insulating fitting from interrupting the ground path and creating a potential difference. When dealing with sensitive electronic equipment in separate buildings, additional measures may be necessary to minimize the effects of electrical noise and transients. This might involve installing surge protective devices (SPD) at each building to protect against voltage spikes caused by lightning or other disturbances. SPD should be installed in accordance with NEC Section 285 and should be properly grounded to the building's grounding electrode system. In addition to SPD, isolation transformers can be used to isolate the sensitive equipment from the building's electrical system. Isolation transformers provide a high degree of common mode noise rejection, which can help to prevent noise from interfering with the operation of the equipment. The secondary winding of the isolation transformer should be grounded to the building's grounding electrode system. Proper documentation and labeling are essential for maintaining the integrity of the grounding and bonding system in separate buildings. All grounding electrodes, bonding conductors, and equipment grounding conductors should be clearly labeled to identify their purpose. This helps to prevent accidental disconnection or modification of the system. A grounding electrode system should also be documented in the electrical panel schedules and on as-built drawings. This documentation should include the location of all grounding electrodes, the size and type of bonding conductors, and any other relevant information. Regular inspections and testing of the grounding and bonding system are also crucial to ensure that it is functioning properly. The inspection should include a visual examination of all grounding electrodes, bonding conductors, and equipment grounding conductors to check for signs of damage or corrosion. Testing should include measurements of ground resistance and ground impedance to verify that the system is providing an effective ground path. Any deficiencies identified during the inspections or testing should be promptly corrected to maintain the safety and reliability of the electrical system. Now let's consider specific scenarios and examples to illustrate the application of NEC requirements for grounding and bonding in separate structures. Firstly, consider a residential property with a main house and the detached garage used as a workshop. The main house has a service entrance with a grounding electrode system consisting of a ground rod and a connection to the metal water pipe. The detached garage is supplied by a feeder from the main house and also has its own grounding electrode system consisting of 2 ground rods. According to NEC Section 250.32c, the grounding electrodes at the main house and the detached garage must be bonded together. This is achieved by running a bonding conductor from the grounding electrode system at the main house to the grounding electrode system at the detached garage. The size of the bonding conductor is determined by the size of the largest ungrounded conductor supplying the detached garage, as specified in NEC Table 250.66. In this case, let's assume the feeder to the garage is protected by a 60 amp circuit breaker and uses number 6 AWG copper conductors. According to NEC Table 250.66, the bonding conductor must be at least a number 6 AWG copper conductor. The bonding conductor is run underground in a conduit to protect it from physical damage. At the detached garage, the bonding conductor is connected to a grounding busbar that is connected to the 2 ground rods. The ground rods are driven at least 8 feet into the ground and are spaced at least 6 feet apart. All metal parts of the electrical system in the garage, such as metal boxes and conduit, are bonded to the grounding bus by using equipment grounding conductors. Secondly, consider a commercial property with a main building and a separate storage shed. The main building has a service entrance with a grounding electrode system consisting of a concrete encased electrode U for ground and a connection to the metal water pipe. The storage shed is supplied by a feeder from the main building and does not have its own grounding electrode system. However, the storage shed does not house livestock and meets the other conditions specified in NEC Section 250.32b for an exception to the grounding electrode system requirement. In this case, the equipment grounding conductor that is run with the feeder to the storage shed serves as the grounding electrode for the shed. The equipment grounding conductor is sized according to NEC table 250.122 based on the rating of the overcurrent protection device protecting the feeder. Let's assume the feeder to the shed is protected by a 30 amp circuit breaker and uses number 10 AWG copper conductors. According to NEC table 250.122, the equipment grounding conductor must be at least a number 10 AWG copper conductor. The equipment grounding conductor is connected to all metal parts of the electrical system in the shed, such as metal boxes and conduit, to provide a low impedance ground path. The equipment grounding conductor is also connected to a grounding busbar in the shed, which serves as a central point for grounding all equipment and systems. Thirdly, consider an agricultural property with a main house and a separate barn used for livestock. The main house has a service entrance with a grounding electrode system consisting of a ground rod and a connection to the metal water pipe. The barn is supplied by a feeder from the main house and has its own grounding electrode system consisting of a ground rod and a concrete encased electrode. Because the barn houses livestock, the exception in NEC section 250.32b does not apply, and the barn must have its own grounding electrode system. According to NEC section 250.32c, the grounding electrodes at the main house and the barn must be bonded together. This is achieved by running a bonding conductor from the grounding electrode system at the main house to the grounding electrode system at the barn. The size of the bonding conductor is determined by the size of the largest ungrounded conductor supplying the barn, as specified in NEC table 250.66. In this case, let's assume the feeder to the barn is protected by a 100 amp circuit breaker and uses number 3 AWG copper conductors. According to NEC table 250.66, the bonding conductor must be at least a number 4 AWG copper conductor. The bonding conductor is run underground in a conduit to protect it from physical damage. At the barn, the bonding conductor is connected to a grounding busbar that is connected to the ground rod and the concrete encased electrode. All metal parts of the electrical system in the barn, such as metal boxes, conduit, and livestock watering equipment, are bonded to the grounding busbar using equipment grounding conductors. In each of these scenarios, it is essential to carefully follow the requirements of NEC section 250.32 and other applicable NEC sections to ensure that the grounding and bonding systems are properly designed and installed. This will help to protect people and equipment from electrical hazards and ensure the safe and reliable operation of the electrical systems in separate buildings and structures. Remember that local codes and regulations may have additional requirements or restrictions that must be followed. Always consult with a qualified electrical professional to ensure compliance with all applicable codes and regulations. Now let's discuss the practical methods for bonding steel structures, emphasizing the techniques and materials that ensure effective electrical continuity and safety. When bonding steel structures, the primary goal is to create a low impedance path for fault current to flow back to the source, thereby minimizing the risk of electrical shock and equipment damage. This requires careful attention to detail in selecting the appropriate materials and techniques for making the bonding connections. One of the most common methods for bonding steel structures is to use bonding jumpers. Bonding jumpers are typically made of copper or aluminum and are sized according to NEC section 250.66 based on the size of the largest ungrounded conductor supplying the structure. The bonding jumper should be as short and direct as possible to minimize impedance. When connecting bonding jumpers to steel structures, it is essential to ensure that the connection is clean and free of corrosion. The steel surface should be thoroughly cleaned using a wire brush or abrasive pad to remove any rust, paint, or other contaminant. After cleaning, the bonding jumper should be securely attached to the steel structure using a listed connector that is specifically designed for bonding applications. These connectors typically use a compression or mechanical connection to ensure a reliable and low resistance bond. Another method for bonding steel structures is to use exothermic welding. Exothermic welding, also known as CAD welding, is a process that uses a chemical reaction to create a permanent metallurgical bond between two metal surfaces. This method is often used for grounding and bonding applications because it provides a very strong and reliable connection that is resistant to corrosion and vibration. When using exothermic welding, it is essential to follow the manufacturer's instructions carefully to ensure that the weld is properly executed. The steel surfaces must be thoroughly cleaned and prepared before welding, and the correct welding materials and equipment must be used. The completed weld should be inspected to ensure that it is free of defects and that it provides a continuous and low resistance connection. In some cases, steel structures may be bonded together using structural bolts or fasteners. However, it is important to ensure that these bolts or fasteners are properly tightened and that they provide a reliable electrical connection. The steel surfaces should be cleaned and prepared before the bolts or fasteners are installed, and a conductive grease or compound may be used to improve the electrical contact. It is also important to periodically inspect the bolts or fasteners to ensure that they are still tight and that they have not corroded. When bonding steel structures that are exposed to the weather or other corrosive environments, it is essential to use corrosion-resistant materials and techniques. Copper bonding jumpers should be tinned or coated with a corrosion-resistant compound to prevent corrosion. Steel connectors and fasteners should be galvanized or made of stainless steel. All bonding connections should be sealed to prevent moisture from entering and causing corrosion. In addition to bonding the steel structures themselves, it is also important to bond any metallic components that are attached to the structures, such as piping, conduit, and equipment enclosures. These metallic components should be bonded to the steel structures using bonding jumpers or other approved methods. The bonding connection should be made as close as possible to the point where the metallic component enters or exits the structure. When bonding metallic piping systems, it is important to ensure that any insulating fittings or couplings are properly bypassed with bonding jumpers to maintain electrical continuity. This prevents the insulating fitting from interrupting the ground path and creating a potential difference. The bonding jumpers should be sized appropriately based on the size of the piping and the potential fault current. Proper documentation and labeling are essential for maintaining the integrity of the bonding system in steel structures. All bonding connections should be clearly labeled to identify their purpose and location. The bonding system should also be documented in the electrical panel schedules and on as-built drawings. This documentation should include the size and type of bonding conductors, the type of connectors used, and any other relevant information. Regular inspections and testing of the bonding system are also crucial to ensure that it is functioning properly. The inspection should include a visual examination of all bonding connections to check for signs of damage or corrosion. Testing should include measurements of bonding resistance to verify that the system is providing an effective low-impedance ground path. Any deficiencies identified during the inspections or testing should be promptly corrected to maintain the safety and reliability of the electrical system. By following these practical methods and techniques, you can ensure that steel structures are properly bonded to provide a safe and reliable electrical system. Always consult with a qualified electrical professional to ensure compliance with all applicable codes and regulations.